So I did my lab on the electrical resistance of fluids. So basically I ran currents through them, and so I wanted to find out what properties of the fluids themselves affected electrical resistance. So not necessarily the properties of the resistor per like one fluid, but the actual inherent properties of the fluid. So this was my setup. This wasn't actually what my setup looked like because I ended up not using these kinds of ammeters and voltmeters because they weren't sensitive enough for the really low currents that I was getting. But my setup basically looked like, it was like, wow. It was like this. And then, so this was a battery, and then I had a light bulb here. And mainly I had a light bulb because at first, when I was trying to use these voltmeters, I wasn't getting any readings, so I was scared that there wasn't any current going through the circuit at all. And so this just showed me that there was, and it also helped tell how conductive my resistors were because it was a lot brighter for fluids that were less resistant. And so I didn't get like any quantitative data from that, but it kind of helped me get an idea of like what was going on. So I thought that the acidity of the fluids would affect the resistance because I knew that like you could make batteries with lemons and stuff, and lemons are really acidic, and I'd read that could influence it, and I also thought the density would affect it because I figured that if the particles were a lot closer together, then the charge could pass through them more easily. So I tested the pH of the fluids, and that's basically what it looked like. So the colors basically changed for what pH it is because I used cabbage juice. So,
This is a chemical technique. You can just use cabbage juice to measure the pH of stuff.
Yeah, so
Wow.
yeah, it's basically a natural indicator. So
That's really
so
cool.
if you boil it, then you get the like chemicals out of the cabbage leaves that will respond to the different acidity of the fluid. And so this I was just testing to make sure my indicator fluid worked. And so that is baking soda solution, the blue one, and that's vinegar. And so the vinegar is really acidic, and the baking soda solution is really basic. So you can see that basic ones are more blue, and the acidic ones are more pink or red. And so this was actually kind of a high error way of testing the acidity because I had to like interpret the color as a number, and so I was kind of worried about that not being very accurate. This is basically what my data collection graphs looked like so this was when I was running current through the resistor, and this was when I took the battery out of the circuit. And so I found that after I took the battery out, I was still getting readings for voltage and current, and so basically they were still supplying voltage after I took the battery out, so they were kind of acting as capacitors. And that's not a table. So my first graphs that I did were kind of inconclusive. This was resistance versus the acidity, and you can see, and it goes on a scale from 0 to 14, which is the most acidic to the most basic. And you can see that the ones that have more extreme pH levels tended to be less resistant, but when they were more neutral, they could either be really resistant or like very conductive. So like this like really low dot here is salt water, which is pretty neutral, has a pretty neutral pH, but it was really conductive. So I had kind of inconclusive results from that. There wasn't like a direct correlation or anything. And then this is what happened when I measured density, or resistance over density. And so the less dense fluids tended to be more resistant. But again, it wasn't really, I didn't really have any obvious conclusion from this because like this was lemon juice and it's not very dense, but it's pretty conductive. So since they were acting as capacitors, I found the capacitance, and you can like the capacitance was a lot higher for lower resistances, which is not what I predicted. But
those are in farads.
Is that okay?
Yeah, those are big capacitors. Like, that's 10 millifarads.
But it's a really small number.
Well, 10 millifarads is a really big capacitance. How did you find capacitance?
I used an equation.
Could you share the equation?
I don't think so.
Okay.
Maybe. It might be this.
It's probably negative.
Yeah.
Okay, maybe there's a C in there somewhere?
Yeah.
Sorry, you have it written in your lab report somewhere.
Yes,
I can look it up. Okay, all right, great. You could just tell me that.
Okay. So, yeah. So basically, it turned out that I wasn't getting any clear data because it's mostly based on the composition of the fluid, and it's not on things that I could measure because current flows through liquids using ions in the liquids, and so I couldn't really count the number of ions. But basically what's happening, I didn't make this picture, I just found it useful. So positive ions in a solution are going towards the negatively charged side of the container, and the negative ions are moving towards the positively charged side. And so so I made these resistors, and basically it's just a container, and you can put fluids in here, and it has wires that connect, or a wire on this side that'll be positive and a wire on this side that'll be negative, so that charge can move through the fluid. And so one thing that I disregarded was the electric field inside the resistor. So that probably caused error because what I had was actually like this. So there would have been electric field lines like this, but in 3 dimensions. And so it wasn't actually like this picture. So that probably caused some error in my lab. This is a really bad picture, I apologize. But yeah, so this actually explains why my fluids with more extreme acidities were more conductive, because acidity is a measurement of the hydrogen and hydroxide ions. So yeah, but salt was an exception because it has sodium and chloride, and so that's not measured by pH, but it still has a high number of ions. So that's not a table. So luckily I could find how conductive they were, because the way that you calculate, or the way you can describe how well the ions will move through the fluid, or will conduct charge through the fluid, is using resistivity. And so that's basically an inherent property of the fluid, so you can't change it the way you can change resistance, but it is directly proportional to resistance. And this is actually a really redundant graph, because I found resistivity using resistance, but it shows that they are directly correlated, or that they are proportional. And basically the equation for the resistivity, the resistivity is resistance times area over the length. And so the area was how big the surface area of this circle, and then the length is the length of my container. And since I kept those constant, they didn't affect this graph. And so if I was going to do this in the future, I would definitely change the length and the area so that I could get better or cooler graphs, because this is pretty boring. But yeah, so in conclusion, the current moves through the liquids through the ions, which can be represented by the resistivity of the fluid. And if they have a higher resistance, they'll tend to have a lower capacitance, and then denser fluids will have a lower resistance, and fluids with more extreme pH have a tendency to have lower resistance, but neutral ones can have low resistance too. So yeah, and it turns out that people run current through water a lot, and so one example of this was that when I was doing research, there was a lot of websites from the Environmental Protection Agency, and apparently they care about like the conductivity of soil and like earth, and so they have a lot of equations using the resistance of the water and how much water is in it, and basically the composition of the soil. So that's interesting. And then electrolysis is plating one metal with another metal. So if you have like a big chamber of fluid and you run current through it and it has some kind of metal ions and you put like a spatula on one side, then when all the ions move towards that side, then it could like cover it with a really thin layer of whatever ions you're extracting from the solution. So like that way you wouldn't have to make it out of like solid gold or something. You could just cover it with a thin layer. So that's really useful. And it's also used in genetics, ionization, because if you have like a gene mutation, then one of your chromosomes will be cut, and so when they run current through a solution with the genes in it, they will all like stack up based on the size of their charge. And if one of your genes is smaller, then it'll go to a different place in the stack, and so you can tell what kind of mutation someone has by using that. So I thought that was really cool. And that's it.
Thank you. We have time for maybe a quick question, if you have an emergency question.
Did you keep the temperature constant you tested? Because
yeah, all of my things have been. I let them all sit out for like an hour so they'd be room temperature, and most of them were room temperature anyway. But just to make sure it was all constant.
Cool. Thank you, Alec.
So I did my lab on the electrical resistance of fluids. So basically, I ran currents through them, and so I wanted to find out what properties of the fluids themselves affected electrical resistance. So not necessarily the properties of the resistor per like one fluid, but the actual inherent properties of the fluid. So this was my setup. This wasn't actually what my setup looked like because I ended up not using these kinds of ammeters and voltmeters because they weren't sensitive enough for the really low currents that I was getting. But my setup basically looked like, it was like, wow, the circuit at all. And so this just showed me that there was, and it also helped tell how conductive my resistors were because it was a lot brighter for fluids that were less resistant. And so I didn't get like any quantitative data. It was like this. And then, so this was a battery, and then I had a light bulb here. And mainly I had a light bulb because at first, when I was trying to use these voltmeters, I wasn't getting any readings, so I was scared that there wasn't any current going through